know that Pedro has recorded a discussion of Clement de Chase Martin and de Hauteville. He did a recording. We're gonna look at the recording. Okay, we're gonna look at the recording. We're gonna do it when we get back. But what I want to do next is Callaway and Santana. Okay, and the reason I want to do Callaway and Santana is because I want to go directly into the simulation. And when I go directly into the simulation, since we just did the bacon decomposition and showed how bad it was, we're going to now look at Callaway Santana and see if it can improve. Okay? See if it can improve. Now, what we're doing now is we're going to be in a world of these weighted manual aggregations. That's probably the right way to think about it. The manual aggregated diff and diff models. Okay. So let's take a break. Let's come back 5 minutes till. This is strange. The Magic Mouse does not have... Does not have a way to get open the stupid thing. Let's see if I know how to... Am I missing something? Do I know how to get the Magic Mouse to open to get the batteries changed? There was nothing wrong with the old way. There's a thing missing. Look. Does that make sense? Am I missing something? Seems like it should be right there, right? Well, that's going to be a disaster. Because this is a big computer, not a laptop. Oh, man. What is there, a charger? That is lame. I don't have it. I got rid of all that stuff. Oh, man. It's too big for lightning. So it's got a smaller. Wait, maybe it's... Hold on one sec. Okay. Okay, let me charge this real quick. Okay, I don't need the mouse right now. So next what we're going to do is the Callaway Sant'Anna, all right? We're going to use Pedro's paper. Yeah, exactly. There was literally nothing wrong with the original way to do it. I have about 50 million batteries for the... Anyway, all right, hey. That, you know, I like to fix things that were working fine. I feel like that's not appreciated enough. So we're gonna do Callaway Sant'Anna. So these new papers, all right. So here's the deal. So Andrew's paper does not solve the problem that he identified. It doesn't solve the problem that he identified. It just points it out. And Callaway Sant'Anna is not the first paper. It was actually Clement's. It was actually to Chase Martin and I think it was the French team's paper was first. But I'm just going out of order because I want to jump right back into my simulation because Pedro's going to do a difference a different estimation with his, and I just want to stick to it. So we're going to look at Callaway Sant'Anna. It's oftentimes these days being called CS. It's still recording. It should still be recording. So new paper. All right. So interesting. Yeah. So interesting ancestry. Callaway Sant'Anna is a descendant of Bodier 05 as well as the double robust paper that we talked about earlier. It's kind of got like the paper's structure is, it's, you know, this is how Pedro's brain thinks, I think. I think it's like he basically always starts in these steps, and he's like, you know, starts with the target parameter, identifying it. What is the parameter? What are the assumptions needed for identification? He starts with some parameter. And then what Pedro is going to do is Pedro's going to take that parameter that he has identified, and he is going to aggregate up. Compare that with what two-way fixed effects did. Two-way fixed effects did no, like, it's like the estimation of two-way fixed effects was like immediately identifying a weighted average. The weights were not, it wasn't like it was taking some individual 2x2 and then taking those weights and then adding them together however it wanted to. It was like just going directly to the parameter, right? But Pedro's going to approach it. He's going to approach it more slowly, and this is something you see in Borsak, Jaravel, and Spice also, which is start with the parameter that you want. That start with this simple parameter, and then build up like a Lego, like Legos. Okay, then figure out what it is you're looking to get, and estimate. Then start the estimation process. Then do your inference. So when are you going to use Callaway Sant'Anna? When might you use it? Well, when you have multiple time periods, you're going to use it then. If you have variation in treatment timing, differential timing, you're going to use it then. If you have conditional parallel trends. If you have unconditional parallel trends, fine. But if you have conditional parallel trends, also fine. Okay? So when are you going to use it? These are the situations. And you ask me if this isn't probably what you were thinking of. Treatment effects that are heterogeneous by time of adoption. Early adopters have different treatment effects than late adopters. Treatment effects that change over time. Dynamics. Treatment effects that are more pronounced in the long run than the short run. Treatment effects that differ for people that were treated in a recession versus those that were treated in an expansion. Phil Oreopoulos has, studies like that. I'm almost positive I said that wrong too. But I don't think I've said anybody's name right. I've said Pedro. So, and even that, I bet that's like not exactly right. So here's the parameter of interest. So we're starting with this target parameter. The target parameter is the group time average treatment on the treated. Okay, it's the group time average treatment on the treated. Expectation Y1 minus Y0 for a group. Now, what is a group? A group is Florida, 2005, Montana, 2009, the 13 states that were adopted in 06. Groups are basically sets of units that share the same treatment date. That's what a group is, okay? So big G is a dummy variable, and lowercase g is referring to that group. It is referring to that group year, rather. So there's a 2005 group. There's an 06 group. There's an 07 group. Okay? So we're going to have here group time average treatment on the treated. There's going to be a bunch of them. All right? So you think about it for a second. Florida, treated in 05. There's a Florida group time ATT for 2005, for 2006, for 2007, 2008, 2009. So that's 5 group time ATTs for Florida. Let's say Louisiana and 13 other states are treated in 06. That's 06, 07, 08, 09. So that's 4 more, and so on. So think about what Pedro's doing here. Pedro and Brant are doing. They're basically going, take the smallest level of the treatment effect that you could be estimating, and then build up to the interesting ones. Build up to the interesting ones, as opposed to just starting at the most aggregated level. Because what this is going to allow Pedro and Brandt to do is to explore lots of heterogeneity. That's one of the things that makes this such a fun paper, is that it opens up the ability for you to do new methodological analysis, stuff that actually you weren't even doing before. Okay, so group time is the ATT for a specific group and time. I lifted the cat up again and I got covered, and good grief, this never happens. It's because I didn't shave. So groups are basically cohorts of units treated at the same time. There's going to be a bunch of them. They're not determined by the estimation method. They're just really simple. They're just differences in means. So you can use lots of estimation methods to get them. And here's the nice thing. There is no restriction about heterogeneity. Nothing about, restrictions about you need homogeneous treatment effects, timing, evolution of treatment effects, gone. Because it's doing it for a specific year and it's doing it for different points in time, that issue about dynamics is irrelevant, because it's always the snapshot. It's always the snapshot treatment effects. And so it's going to provide a way to aggregate over those to get, let's say you want to get a single ATT. Well, he's going to show you how to do it. You can get weighted average overall 25 group time ATTs. Maybe you only want to get average treatment on the treated for the early group, for the late group. And the inference is going to be either analytical, standard errors, or bootstrap. I say right here the bootstrap. I actually thought it was the bootstrap for the longest time, and then I started noticing that there was analytical standard errors. But anyway, we'll use the bootstrap in our example. I have to catch up. What am I missing? Oh, okay. Notation. T periods. You're either treated or you're not treated. Once treated, you cannot revert. Pedro's going to talk about a paper where you can revert. G is a dummy. Capital G is a dummy. Lowercase g is the year of treatment. C is binary. Means you're in the control group, equaling 1 if never treated, or it can equal 1 if not yet treated. Okay? And then the generalized propensity score. And the generalized propensity score is basically the probability of being in a particular group conditional on X, baseline X, just prior to the year of treatment for treatment group and control group. Okay, so it's going to be the treatment group and the units not yet treated or never treated. Okay, you have propensity scores. So you have different propensity scores because the probability of being in group in the 1986 group might be different than it is going to be different than the probability of being in the 92 group, and the probability being in the 98 group, and the probability being in the 04 group. So here's the assumptions. Notice again. See, here's the big deal about this diff and diff stuff. For the longest time, we just thought we just had to deal with we just really thought that it was just parallel trends. That's why the dominance of that event study, I think the dominance of the event study was really like born right out of that parallel trends, because people were willing to look at the pre-trends to check for those identifying assumptions, those untestable identifying assumptions. But in reality, we've got some more. So here we have some more. So sampling is either panel data or repeated cross-section, conditional parallel trends for the never treated or the not yet treated, irreversible treatment, common support, limited treatment, anticipation. So this is a new assumption that shows up a lot in these papers. They call it the no treatment anticipation. That kind of ends up being built into a lot of what we were doing already. Here is the estimator. This is the inverse probability weighting estimator, but the doubly robust would just add in here that into that, I can't actually scroll over, but instead of it being y minus y, it would be that y minus y minus that that outcome regression approach. Okay, so this is the inverse probability weighting estimator. So what you've got here, let me see if my mouse has been sufficiently charged. Okay, so here's what we got. We got the differences. All right, so we got differences. Let me just look through the notation. So this is like at some particular year. All right, so let's say it's like, say, group 1 is treated in 1986. That's 1986 right there. Let's say we want to know what the group time ATT is in 1988. So that'd be 88 minus 85. So the baseline is always going to be the year prior to treatment. Okay? So you're going to get it for treatment group and control group. You know that because when G is 1, this whole thing here goes to 0, and it's just going to be, the weights are going to be on this. It's going to be 1 over that. And when that's a 0, that's a 1, and the weighting of the control group is going to be by this. Okay? So what we really need to do this is we need to calculate these weights, and just multiply them by these differences, these before and after differences. All right, so aggregated versus single year group. So the method they propose, the only thing it's doing is it's estimating a specific ATT per group time, the 1987 ATT for group 1, the 1989 ATT for group 1. I mean, you could have 100 of these, right? You're not going to present 100 of these, right? It's going to be a nightmare. So what you're going to do is you're going to aggregate up to the parameters that you think are interesting. Might be the total ATT, might be the total ATT for group 1, might be the total ATT for group 2, might be the ATTs for your event studies. Okay? And then we're going to have inference with the bootstrap. So let me show you this. This is great. So, let me get all this stuff here. All right, so what we've got here is I'm going to manually do Callaway Santana a couple of times. Scott Churchton, is the year prior to treatment always the baseline? It is always the baseline. And I don't know if it's to exactly get rid. I mean, it seems like this came straight out of, well, G-1 is the pre-treatment. That's what it is. I mean, it's basically pre-treatment. So, they're treated in 1986. So you have to go, before. So that's what it is. So you could have a treatment effect in 1986, the year of treatment. And so they're trying to do that. They just have defined, the baseline in terms of treatment year -1, if that makes sense, Scott. All right, so what we need, look at what we need here. Okay, so I'll just keep going back to this a few times. So, oh gosh. So here is a 1. Here is the expectation, the average of one of the number of. So we need to get a 1 first. Okay, so we did that. We got dummies for each group. We need a propensity score. All right, so we're going to do this for the 1986 group. And we just all we have to do is construct the data in such a way that we're getting only the not yet treated and group 1 in the same sample, and then we'll just estimate a propensity score. So we're going to go if year equals 1991, all right, and it's either group 1 or units not yet treated. So look at what time. Right, so this is basically time till is the number of years until they're treated. All right, we're going to estimate that propensity score. We don't have any covariates, so look at what we end up getting. So it just got regressed against the coefficient, 0.25. So it's just like, why? Because there's 4 units, 4 groups. What's the probability of being in group 1? 1 divided by 4. Now we got to get our post and pre. Post, pre. Now we're doing this for the 1986 group time ATT. All right, we're doing it for the group time ATT 1986. So we got to get post 1986, pre 1985. Okay, we need to get this right here, mean G. So we'll do that here with the egen command, mean G1. All right. Then we've got to get the mean of this. Okay, so that's going to be the mean of the propensity score as that ratio. All right, that's no big deal. We just took mean and we just wrote out the formula. We're getting there though. All right, ultimately at the end of the day, this is all that he's doing. Then we're going to get our weight here. Then we're going to get this weight. Then we're going to weight each individual Y for the treatment group and the control group. Okay, so we did that. Then we're going to calculate the ATT, the group time ATT. It's going to be the 1986 group right here. 1986 group in 1986. All right, so we know what it is. It's a 10 because remember. Go back up here. 1986 minus 1986 is a 0 plus a 1. 1 times TE. TE is a 10. Okay, so this should be a 10 if he did it right. 10. Okay, maybe he got lucky. Let's do it again. Let's do the 87 one. Go through all those steps again. This one will be a 20 because it was supposed to be 1987 minus 1986, which is a 1. 1 plus 1 is a 2. 2 times 10 is a 20. 20. So you see what we're getting here? We just got the first ATT. We got the second ATT. We could keep going. Let's do one more. This should be a 30. 30. So we're getting these individual group time ATTs. We're getting all these individual group time ATTs. And once we get these individual group time ATTs, we can add them together and get whatever we're after. All right, so look what I've got here. I've got this R code right here. Let's first look at the syntax, okay, for, let's look at the syntax for the DID command. That's Callaway Santana. All right, so this is an R. Now I only need read stata 13 because my data is going to be in stata format. I'm going to use ggplot2 to make these pretty pictures. And then I got DID. Okay, so this is Callaway Santana applied to the Ching and Hoekstra paper. All right, so first I load the data in, run. Okay, then we've got our commands here, ATTGT, outcome, time variable, panel variable. So these are variables in the actual data set. There's an outcome called homicide. There's an outcome called year, or a panel year identifier called year, panel identifier called SID, effective year. So this is our G. This is our G. This is the year of treatment associated with each group. Name the data. No covariates. So I say null. So if I had covariates, I would get rid of that and I would list them out here. But I'm not going to do that. I'm going to use the doubly robust method. I'm going to use as my control the never treated. but I could have used the not yet treated, right? I'm going to use the bootstrap 1,000 times, and I'm going to cluster my standard errors, or cluster by SID. So here it runs. Now it gives us a little bit of some warning messages. It's saying, be aware there are some small groups in your data set. Remember 05? 05 was only Florida. 09, Montana. Oh, sorry. Okay, so I ran this right here. I have all, this is the syntax. It's really straightforward. Once we've got it, it's all being stored in one of these, files over here. And so it's telling us here we need to be a little bit careful because we have small groups. We have small groups. Okay, so let's look at the total aggregate ATT. Okay, so this would be the average ATT over all individual ATTs that I've estimated. All right, so you get a 0.1084. Okay, you got a star here telling you significance. You got confidence intervals. You got a standard error. Okay, so I've got this overall ATT, and what it is it's the weighted average over every single ATT, of which there was like 5 for the 05 group, 4 for the 06 group, 3 for the 07, and so forth, right? And it was like, all of them. Okay, I don't understand this. What was small groups again? States? No. Small groups are only a few units were treated in that year. Okay, so only one state was treated in 05. Only one state was treated in 09. It will still estimate it. Okay, it's still going to estimate it, but it's going to say, be aware that there are small groups. Okay, so what we get first is this overall ATT. But look what else we get. This is really cool. We also get ATTs per group. Yeah, everything's the same if you get repeated cross-section. It just will take longer. It just will take longer. Victor, what's the problem with small groups regarding estimation? That's a good question. If Pedro was on, I don't remember why that ends up being a problem. I think that it is probably going to have something to do with variance, but I meant to sort of look that up, and I don't remember. It's still going to give you a group time ATT, but I guess it could be a little volatile or something like that. So look what else you get though. You can get the average for Florida, just for Florida. Okay. So remember, Florida was in 05, so we got a 05, 06, 07, 08, 09, right? Add them all together, divide by 5. 0.0931. You can get it for 06. You can get it for 07. You can get it for 08. Now, you can get it for 09, but the thing is, 09 doesn't really have any post-treatment data to work with. Okay? You can also get each individual group time ATT over time. You can get the event studies. So like, for instance, let's do this. Having a little trouble here because I forgot how to, there it is. Okay. So you got here the group. So look, you can get the event study plots for each individual group. There's the 05 group. There's the 06 group. There's the 07. It looks like really 05 is doing a lot of the work. You're getting a little bit from the '06 group because right here looks like those are marginally significant. '08, '07, that's not really doing. You got one here in '09, a little bit of one in 2010. This kind of helps you. What you're able to do here is just explore a lot of what you're getting is you're just getting the ability to explore a lot of the heterogeneity a little bit better. You can also do the event studies. Let's plot that. Here's the event study. Now you get all these right here, but you've got, for that simple kind of estimate, you've got this right here. You get this treatment effect. So Callaway Sant'Anna is really nice. It's consistent. Is anything changing if we add controls? Yeah, the propensity score. The propensity score and the outcome regression change if you add in controls. Yeah, they were, Sarah. I think actually they were pretty similar. See, now here's why I think Ching and Hoekstra get such similar effects as everybody else. Ching and Hoekstra have a large number of untreated, never treated units. The larger the number of never treated units, the less of the influence of these individual 2x2s that are coming from the already to the let's see, already to the treatment to the already. I want to show you something. Okay, so let me run this myself. Here we go. All right, so this is going to be the Bacon decomposition on the Ching and Hoekstra paper. Watch this. Now he's finding, okay, treatment effect of 0.069. Callaway Sant'Anna found a 0.075, right? So remember, the two-way fixed effects has that attenuation bias, so it was pulling it down a little bit, at least from that. Now, what is contributing? What is contributing? Right? You've got the not yet treated has a weight of 0.07. You got the forbidden 2x2s here. Later to early, weight of 0.024. Most of it's coming from the never treated. So the bigger your reservoir of never treated units, probably less of an issue even when you have heterogeneous treatment effects over time, because those forbidden 2x2s end up not really being that big of a problem. Okay? All right. So what I'm going to do now is